you can start. That's not a problem.
So I start. Huh?
Yeah.
So we have good afternoon, everybody. So we stopped here and we have to continue now. We have introduced the different forces which act on the droplets. And we have a series of forces. We name them the drag force, the surface force, the virtual mass force, and the Bassett force. We had also the gravitation force, the Magnus force, Huffman force, and we can also have the electromagnetic force if necessary. And I was up here, and the question is how we can consider also thermal effect. And in the previous lecture, we have introduced the thermal relaxation time. I recall it here, and we did a relationship between the thermal relaxation time and the dynamic one. This is only to remember you, and then we can continue by seeing how we can transport the spray and while accounting for the interface coupling. We introduce the Lagrangian tracking with the related forces which act on the particle, but we have two phases. Then we have also to see how we can describe the Fourier phase from the mechanics and the turbulence. So we know that for single phase or for mixture, something like that, we have the classical governing equations of thermofluid mechanics like this, the continuity equation, the moment equation, the energy equation, and also concentration equation. So I recall you that this is the mass density, the velocity, and we have here the pressure, and it was tau, these surface forces, the scalar part and the viatoric part, and we had here the gravitation force. Now we have the total energy equation, now the internal energy equation, and we have the heat flux, and we have here the dissipation part and radiation part, and also the concentration equation. We have naturally this part is everywhere is the convective part, the diffusion part, and here the chemical source term. So we can naturally now apply this equation to the two-phase flow. And if we apply this for two-phase flow, we'll come out with this equation where we have some additional source terms which are responsible for the interaction between the two phases. This means that the effect of the dispersed phase on the Fourier phase. In the case we have evaporation, we will have additional contribution here, and we have here the sum of all contribution we put here, and for in the energy equation too, we will get this source term here, and in the concentration equation, we will get also this source term. So here replaced by C. To make everything consistent, thermodynamically consistent, we can also add the so-called the entropy equation or the entropy inequality equation if we account for the fact that the prediction of entropy is always positive and equal to 0 for equilibrium process or reversible process. And this equation, this set of equations, we can put them in a generic expression like this one. Where psi will be rho, will be the momentum or the energy or also the concentration, everything we would like to track, or to describe like kinetic energy or dissipation or Reynolds stress tensor, etc. So for the Carrier phase, we can have in mind these two sets of equations. Normally people use only this one. Sometimes I include this one to see if the model we will use to describe different processes are thermodynamically consistent. But in this term, which is a generic term of this, we have different sources. We have the classical source term here, which consider the non-convective contribution, non-convective diffusion term, like like the Cauchy stress tensor, that this one here, and the scalar flux. And this one accounts for the presence of particle if we don't have evaporation process or phase changes or chemical reaction. Here, if we have the evaporation process, this one can also be the source term of chemical reaction. So we have this set of equations, this one, and also our transported equation for the particle. I think Professor Shoke has introduced the turbulence. So we know now that we have different classes of turbulence modeling. We have the RANS modeling, we have LES, and we have also PDF, transported to PDF, and different kind of resume PDF we can have to account for the interaction of turbulence and chemistry. If we restrict on the RANS modeling, then we can have, for example, for the turbulence, we have the K-epsilon model, explicit equilibration model. We can also have the two second order momentum, second order turbulence model for not only for the turbulence, but we can also have the same for the mixture. So for the droplets, I will come back to this. We will have the influence for the turbulence on the particle. We have seen this micro process, which is the dispersion process. And we will find different models, and we will take into account these models. And we did also, in the previous part, evaluation of the interaction between the Carrier phase, turbulent Carrier phase, and the droplets phase or the liquid phase. And depending on the Stokes number, we can have the modulation of the turbulence of the Carrier phase. And now we will focus on this one, where we will account for the phase change. And after that, we will include the combustion. We can also take into account the collision and coalescence. So let me now go through and to remember you everything we did. So this is the turbulence modeling here. This is the dispersion process. And here we will have the coalescence and collision. So to sum up what I put there for the Carrier phase, we see the effect of the dispersed phase on the gas phase. It is here given by this part without evaporation. With evaporation, we can also have, and here it is the combustion contribution. For this subgroup, for this additional term, so we need models. Now here, I include the modeling for turbulence. This means that we did directly here the averaging or the filtering, averaging with respect to RANS, filtering with respect to LES, And that is what we get at this level. So that is either filtering or the averaging if it is favorable averaging. So we notate them in this way. And we have here an additional source term which needs to be modeled. And to make everything consistent with the second law of thermodynamics, we can also try to average this or to filter. If we do this, this is the second law of thermodynamics, the entropy inequality equation. We have this production, we have this term. So we have the first term here, and we have the scalar flux, the turbulent scalar flux. We have the prediction. And also we have some additional equations which account for different processes we can have in our in our turbulent flow. It can have the mass transports, continuity equation, momentum transport, energy equation, enthalpy equation, and other kind of turbulent quantities which can be transported. And everything should be positive here. And we use here, I think it is a methodology from the from the continuous mechanics, in which we say that the entropy inequality is a filter for different processes. Only processes which are consistent with or compatible with the second law of thermodynamics is acceptable. And these processes are thermodynamic process because they are consistent. They are compatible with this second law of thermodynamics. Now, all these equations, all these processes, continuity equation, momentum, etc., can be considered as constrained to fulfill this equation. And because they are constrained, they are connected to this equation by means of such kind of Lagrange parameters. But I will not go into details. People who are interested in can contact me in particular. So this is the description of the gas phase or carrier phase. And we have the dispersed phase. We know that we have to track the particles to solve first the momentum equation for the particle, the motion equation for particle. We know the different forces. We can quantify also these forces. But from this solution, we can get also the position, the evolution of the position, the time. So we can also we can then obtain the trajectory. So in this equation here, we need these source terms. This source term for, if this quantity is 1, then we have the continuity equation, and we will have the source term here. If it is the velocity, then we have momentum equation. Then we have to find out how this quantity. We have now here to account for the source term, and if we have the Lagrangian tracking, what this means? This means that each particle should be tracked along its trajectory, and let's consider this control volume, and we consider this particle here. This means that the change of the momentum of this particle from this position to this one, to this time step to this one. So this change of momentum will be gained, will be transferred. Yeah, let me say it will be transferred to the Fourier phase. And for this particle too, for the other particle, for all these particles. so that we can sum this change of momentum of particles while traversing this control volume. We have to time step n plus 1 minus n. This is this n, and this is n plus 1. This change here is this change of velocity multiplied by mass. Then we have the momentum change of these particles, and we have k number of particles, and we multiply by the number of these particles. And we can also make an average, a volume average, and we divide by this volume. This is for the drag force. And if we have also the gravitation force, we have to take also the change of the gravitation force during this time step. And this provide us the source term we have to put here in the case we are dealing with the momentum equation. This should be done for all the quantities, for mass, for momentum, for energy. And as I write here, we carry out the averaging along the particle trajectory and for all particles which cross the control volume. So if we understand this, then it is very clear for everything, and we can give an application here for rounds. If we don't consider the phase change and chemical reactions, this means that in this equation, the chemical reaction part and also the phase change is not included in this term. And here we have the classical source term, as I told you, the non-convective flux. Then we have the reduced equation in this form. P may be 1 for the continuity equation, and for that without phase change, this quantity here is 0. If we have the velocity, then we have the momentum equation, and we have to define this term as we had it here. And the flux, the diffusion part is this one here. We have the diffusion, and no, I put them here together. We have the diffusion first, the phi, and we have the diffusion here. This should be the the turbulence part of what we obtain here. This is this part, and we have also the gradient of the velocity. Excuse me, I have to check it. No, this is the turbulent part. Yes, it is the turbulent part. So obtained by making the gradient of the gradient part, and here the not the deviatory part, the deviator part, and this is the turbulent part. Excuse me. This is the turbulent part in this diffusion part. So we have the molecular viscosity and the turbulent viscosity. And this is a source term we had obtained before. And in the case we did with the chi epsilon model, then we have also the source terms, these non-convective source terms. We have this one and this. This is also related to the turbulent part, and this one is the source term, and the diffusion part is this one. And for the epsilon equation, we have the prediction of the diffusion, dissipation part, and we have the source term, and here we have the diffusion. So I introduced this factor here. This factor account for is what we introduced yesterday, the particle volume fraction. This means that if you have the particle volume fraction here it is the liquid volume fraction. It accounts for the space occupied by the particle within the system. So because we deal with chi-epsilon model, in our case, we have different coefficients. These coefficients are here in this. This is this here. We have say mu, this is this one. We have also these different coefficients in different term. Here we have also we have these coefficient. We have CF. This is not CF. It is sigma K. Excuse me. And here we have also a sigma epsilon, which is forgotten. But the coefficients are clear. It is the C mu. It is a C1 in the K epsilon equation C1 and C1, and we have here for this gradient expression in the turbulent diffusion part. So to summarize everything, that is what we did, the discrete coupling, okay? And now we have to deal with the different source terms we obtain here for the momentum. We have to obtain also for the K epsilon. And for K, it is not very complicated. So we know that to obtain the turbulent, to obtain the kinetic energy, we have to multiply scalar to make a scalar product of the momentum equation with their velocity. And from this, we can obtain a kinetic equation. This is what we do here. By doing this, we multiply this expression by the velocity, and we separate it in mean part and fluctuation part. And this is what we do here. So we multiply by the viscosity, by the velocity, scalar, this quantity, and we carry out the averaging procedure. We have this part minus this one. And for the dissipation, so we know that from dimension analysis, we have the source term here, and we have to multiply the source term by epsilon divided by K, and we have this expression here. So this C epsilon 3, take these values so from some fitting analysis with the experiment. So the problem is now how we can correctly account for the modulation. If we use this expression, this means that we will only dissipate the kinetic energy. And in the case we have wake turbulence effect, Groh and Gillan, 1998, use the Eulerian expression and derive this expression here. I will give you the reference in our paper. You can find all these details. But the source term for the chi-epsilon model was obtained by this expression to account for the prediction of the turbulence in the gas phase once the particles are large, where we have wake turbulence effect. We have the first part, it is a relative velocity, and this is the correlation between these velocities here. And the B is represent only here bubbles, because Groh and Gillan did it for bubble flows. By having this from the Eulerian representation line, try to reformulate this expression in Lagrangian form, and you obtain this expression here. This expression, if we compare with this one, is almost the same, where we have, but we have a coupling effect. This velocity here, the flow field, is replaced by the particle phase. And here, this is the mean velocity. It is okay, but here we replace it by the particle phase, the particle velocity only. And this is the part which account for the wake turbulence effect. And this expression was obtained based on the first law of thermodynamics, in which he account for the conservation of the total energy, and he hoped that with this, the distribution of the energy has been accounted for correctly. And this is also correct, but if we account for the effect of dissipation, then we must account for the second law of thermodynamics. So I summarize all these source terms that consider this. This is the extension in the case we have evaporation. We will come back to this part later on. So we have, if we have 1, we have 0. This is what I have already explained in the x direction. It is in y direction and the z direction. So direction, and this is 0 here. It is also 0. For the temperature, we'll obtain exactly the same this here, multiplied by the heat we have put there. We don't have a chemical reaction or evaporation process. We have kinetic energy. It is what I explained you. And we have dissipation. It is what we got here. And if we have a second order turbulence modeling, then we have to account to enlarge this, but we don't consider this at the moment. I provide it for your information. So having this, then we put everything now together. So this y and z is not here, but I put it in the correct way in this expression. And for k and for epsilon, it is clear we have to multiply by this factor. Then we have the standard projection. It is what we have by multiplying the momentum equation by with the velocity. It is what we got for k and for epsilon. It is what Grow and his collaborator obtained based on the first law of thermodynamics. And here we use the expression by line. I have shown you here this expression here. And in the past, we observed that using only this model, we could not be able to capture the two effects. The attenuation effect if the particles are very small, and the enhancement effect if the particles are very large. That is why we develop new modulation models based on the second law of thermodynamics, and we call it thermodynamically consistent modeling of the turbulence modulation. We did it with our colleague Amadi from US, and we obtained this expression here, which had this additional term to what Grow has obtained, and we also transform it in Lagrangian formulation. So we compare this expression based on the first law and this expression based on the second law. We see that the first term is exactly the same, but the second term is not the same. Here, we obtain like a summation between this one and this one with a factor which account for this distribution of which account for the size of the particles. And this is obtained here. Beta, it is proportion to epsilon prime. Epsilon prime is a quantity which is related to the size of particle to relative size of particle. And using this expression and this expression allow us to be able to see which model is the best one to account for the modulation process. For that, we have to solve the equations. And to solve the equations, we have two sets of equations. We have the Fourier phase governing equation, and we have also the disperse phase tracking equation. So we call one the Lagrangian one, and the other is Eulerian. Here we have not only initialization, and we provide the boundary conditions. First, we have to calculate without source terms. This means that we have only the Eulerian. This means we track first the flow field without accounting for the presence of particles. Then we get this, the velocity here. If you can, let me go back to show exactly what happened there in the tracking. So we are here, and in our case, we use only two forces. We use this force and this force based on their properties we have derived in the model. So here we need the velocity of the flow field, and this velocity for the flow field will be obtained by solving the Fourier phase transport equation, the governing equation of the momentum for the Fourier phase. And we'll come back to the dispersion model, but here I show you the main procedure to capture the procedure of the solution. So once we have the velocity, we put it in the forces. So this means in the drag force. And this allows us to track the particle, to solve it, to get the velocity, to get also the position, and also to get to be able to account for the source term, because we will be able now to have this velocity here and to put them here so that we can calculate this source term, which in turn should be introduced in its equation, this transport equation here. We have to introduce this. So once we have this, we compute the flow phase under consideration of the source term we obtain from this. And if it the running is convergent, then we obtain the solution. If not, so we have to do the different iteration to get a convergent solution. And if we have it, we got the result. Sometimes the source terms can be very huge. If they are very huge, so we use some relaxation tricks to get the solution in a very nice way. And this relaxation means here that we have to introduce the source term step by step to get a stable solution and then convergence of the procedure. So if we are interested in the convergent solution and in this, once we obtain this, once we have this, we can now go to an example. We carry out this experiment in our institute. It was in 2004. This guy is now doctor and is working somewhere. The idea was to generate a grid to generate a grid-generated isotropic homogeneous turbulent two-phase flow, where we have air and glass particle, and this glass particle had different diameters and also different density. But here I put for the same density, and this is the loading. What happens? So we have the cylinder here, and we have our cyclone, which allow to separate the particle and the gas. We have the channel segment for homogenizing the flow. It is these three. What way it is again? It is this one here. No. The two. This here we have here grid, some grid to make our turbulent homogeneous, and it is the measurement section, and we have naturally the filter here, and also we have the compressor to make our system running in a correct way, so that we have enough air to carry out our particle, and these particles are seeded here from this cyclone. So here that is for the measurement. We have some laser there, and the computation domain. This is represent this part here. We have the inflow condition for the mass flow rate, and here for also the flow rate. So this is what we had. Numerically, we have 300,000 control volume. The Reynolds number was this year, and the number of nodes. The number of nodes was 50, and here we have the computation. This is for our grid here, and it is for the computation grid, and we have the inflow condition generated by a method we have developed in the previous time with Klein, so-called the turbulent digital filter to generate inflow conditions. So we have A that is without particle, and the other, so we introduce different quantity of different diameter of particle with different loading. So these are the same here. Yeah, everything is CC, and here we have large particles. So we have B and we have BC are the same, and here we have our large particles. Having this, we carry out first using K-epsilon model the simulation with without particles. It is what we call gas phase. Gas phase is our flow without particles. And Traeger gas is a carrier phase when we have particle within. First, experimental data here without particle, and with particle, we see that for small particles, so we have a dissipation of the kinetic energy. And if we have large particles, we have augmentation of the kinetic energy. Now we see how the calculation produce this by using this standard model. The standard approach means that we have only used this approach where we have the classical determination of the kinetic energy. We multiply the momentum equation with we carry out a scalar multiplication of the momentum equation with the velocity. These normally provide only dissipation of the energy, and that is what we see here from this calculation. it dissipates a lot. And here also, instead of providing this, it dissipates also. If we use the model based on the first law of thermodynamics, we see that the first part is correct, and along the channels, we have augmentation of the turbulent kinetic energy. But for large particles, we obtain a little bit good prediction of the augmentation of particles. Now we use the this model, which is thermodynamically consistent, means that it accounts very well the irreversibility processes within the system. So in this case, we obtain that for small particles, you obtain the correct behavior of attenuation of the turbulent kinetic energy. And for large particles, you obtain also a correct augmentation of the particle due to big particles. So in the past, we tried to publish this, but it could not be possible because the reviewers told us, now, Amzini, you have tried to use the configuration you carry out, and perhaps you have you tune all the parameters to get such kind of agreement. So then we say we will take the configuration by 2G, the well-known two-phase Flowman. So I use also the result here as I gave it in the literature list. So they carry out this experiment with clean air, and here the particles are fed, and we can measure here the turbulent kinetic energy and also the velocity. For three group of particles, the first one is the clean air. This means the gas phase without particle, and then the feed particles, small particles of this kind of diameter, and here large particle with this kind of diameter. So the density is almost the same, and the particle loading is also the same. And we compare with these three models. So for the mean velocity, we don't see a big difference. So that is the standard turbulence modulation model. It is our model, and this is the core model. So we see that we obtain almost the same with a profile for for this flow, for small particles and also for large particles. The mean velocity is not really changed. But if we go to the turbulent kinetic energy or the fluctuations, we see a large change. This is without particles here. Without particles is green, and blue is with particles. So with small particles first, and we see that using this classical, this standard model, so it dissipates as it is expected, not clearly as it should be. And by using the core model, this model enhances the prediction because it accounts normally for the wake prediction, even if this wake is not present. And our model to this blue one, so we obtain the correct behavior of the attenuation. For small particle, let us see for large particle. And for large particles, so the model we have developed also accounting correctly for this effect. And the standard was dissipate always. And this one, as it provides only the enhancement, so it is here correct, but not for this small particle case. So this means that if we use bad model, to account for these different microprocess evolution. So we will get also wrong results. And that is why it is recommendable to check the models we have to use. And in order to check, we must also be able to know first which kind of microprocess we have to account for. And we did it with runs here. Now I will show you for LES. I think that you know what it is. And here I show you directly the gas phase treatment. So we have the continuity equation, the momentum equation, everything with this source term. So what we have introduced here, the source term is 0 because we don't have evaporation. And introducing this source term here, in which we know that also the turbulence should be modeled. So we need model for this subgrid scale model. And for that, what we use the Pythagorean model, but we use also the Yoshizawa model, which allow us to include the one equation model. And in this one equation model, we have the source term as we did for the K epsilon, and we know how this source term should be. Either can be standard model or GROW model or our model. And this is what we integrated in this study. So the model coefficients are derived by dynamic German procedure. So let's now see the two-way coupling. So why it is two-way coupling? Because we have here the effect of the fluid flow on the dispersed flow through this drag force, and we have the effect of the momentum of the particles on this Fourier phase in the momentum equation, and here in the K epsilon in the subgrid scale turbulent kinetic energy equation. So, but people normally do not include this term. It is not really correct, and we will see why. Because we neglect some real processes which modify sometimes the results. Okay, that is our tracking procedure. We have the the position modification of the position. We have this velocity, and we have the momentum, the sum of forces. This is total force. We have here the drag force and gravitation force. Here that is our relaxation time, and this is our drag coefficient. And here we use this relationship, this correlation for that, in which the particle Reynolds number is given by this. And to account for this term, so we know that using LES, we have only this term, but we miss this term. And to account for this term, this means that we account for the dispersion of the particle. When this dispersion is important, it depends on the Stokes number. We will come back to this later when we will discuss different aspects. And we use this here by accounting for only the subgrid scale kinetic energy, and we put a model coefficient. So if we don't use the one equation model, we can also assume that the subgrid scale kinetic energy is provided by the Lilly assumption. It is comparable to what we have in the K epsilon model. So here we use this equation, the one equation model. Why? Because in this we have the possibility to account in a fine, in a nice way for this effect of particle on the on the disperse phase, on the Fourier phase, excuse me. So by doing this, we obtain the same result like we obtained there, but here I show you for other application for the swirl dispersed two-phase flow. This is a configuration investigated by Sommerfeld. We have the particle here, we have the co-flow, and the particle which are injected here are one times they are non-evaporating particles, but after that we use also some isopropanol, but isopropanol will be shown when we will consider evaporating cases. So the diameter is this, and this is the south mean diameter, and we have we consider this distance here. This is our, this is the range of the diameter we are counting for in this test section. The flow velocity, the axial velocity, this, the gas temperature, this, and we didn't consider, we considered the Smagorensky model and we didn't consider the modulation. First, to show only if, to show when we have swirled flows, sometimes it tries to reduce the effect of modulation because due to the swirl, if it is very strong, the particle will follow the flow field. So this is the result. So provided we have the mean diameter and we have the flow conditions provided by this here. We have in part and outside part, we have the inlet Reynolds number, and here we have the density of the particle, the mean diameter, and here the mass flow rate for the particle. And we have this configuration in which we try to provide the result for this axial position. Okay, and the results are provided here. First, for the for the flux of first for the mean radius, the distribution of the particle size, and here for the mean flux of this. I hope that you see this green line, which follow exactly the point, the dot, which represent here the experimental data, so that the LES is really a very good candidate to deal with two-phase flow. The other one is this fairly dispersed two-phase flow, in which we try first to account for, excuse me, this one is not a swirl one. It is only dispersed two-phase flow. The idea was to put the swirl, and here we put the swirl. And by putting the swirl, we have first this recirculation in the middle and also in the corner. And after that, we see the effect of the swirl. So the flow field really exhibit this swirl motion. And here we have the standardized surface of a constant pressure, which represent the axial velocity. And if we see the distribution of particle close to the nozzle, and here way to the nozzle, we see that there is a clear dispersion of the particle within the system. And here we see clearly that we have at these two positions, this close to the nozzle, and this one is very, very far for the nozzle. And we see that it is possible using this Eulerian Lagrangian coupling and using the correct also models to get the good behavior of such kind of two-phase flow system. It was without evaporation. And here, if we have to go to details on a different results, or if we plot the axial position, we see also for the mean velocity axial, for the error mass, we obtain also correct results. And here for the error mass, for that, it is not axial, it is radial here. It is the radial velocity. We obtain an yeah, what it is here. Let me take a look. The radial, yeah, yes. This is the radial here. The radial, not the axial, so I put them together. This is the axial and the radial. And for the dispersed phase, we have also the same. We have the distribution of the radius, and we have the flux with the distribution also of the radius here. And here we have the flux in mid flux. I think I did a mistake here. So don't consider this, but we consider this part. I'm sure with this, what is the mean flux of what? You know. So we take this, I will correct this part here and send to you again what it is exactly. So this is the part we have without evaporation. No, so I get it, excuse me. So we have this different axial position. We have, okay, I see. So the different axial position, it is axial velocity, it is the same. The axial position at different axial positions, it is exactly the same. When we are here at this position, we are 3 millimeter, and here 52 millimeter, 110 millimeter, and it is exactly what we have here also. 112 millimeter and also 155 millimeter. So we are going through from the first position here, going up, and we continue, and we will continue in this area and also in this. So this correct, everything is axial velocity going from bottom to the top here, and there. It is also the same here. We go from bottom 3 millimeter and we go up, and we continue from here to there. Nice, thank you. This is the first part I would like to show you. We will continue, and I give you time for some questions. Have you questions? Otherwise, we will continue with the first change. So I see one question. How to get the volume flux? The volume flux, it is only the volume flux. What do you mean with volume flux? So the volume flux, I don't understand what you mean. The flux is always across a surface. Okay, as you see the unit here, it is per meter square and not a volume. You can precise your question. disperse phase volume flux. You can only obtain something like volume if you do it within a time step. So this means that you have your flux through the surface and you multiply by the time step or by the timing you would like to consider. Then we have a kind of volume. Otherwise, I could not understand. Okay, other questions? We have other question? Yes, I see another one. I found some data from Dawn and they mentioned volume. So we can discuss perhaps about this later on, and we can see what they mean with volume flux. So the flux is per square, meter square, and if you have a volume, then you have to divide by the volume. But I'm trying to understand what they mean with this. So there is another question. So that is what I say. So this means that they consider the surface and they consider this surface per unit of time. Okay, then it is a flux like this. It is exactly what is here. So this is a surface multiplied by per unit of time. Then is, if you want, you can say it is a volume flux. Okay, but you do your flux through the surface and you scale it by the time, then you have it per unit of time. Yeah, because if you multiply the surface with the time, then you have a kind of 3D, kind of a value. So you can say this. Okay. So that is clear. Are there some other questions? Okay. So if you have other questions, so you can keep them and put at the end. Let us continue with the next part, in which I would like to introduce the evaporation part, the phase change phenomena, and the mixture formation. For that, we'll speak about the heating evaporation modeling. For singlet component, I will base on the singlet component, but I will give you perhaps some idea about multi-component if you are interested in it. We'll speak about some turbulence dispersion models, but this will come later on. And I will introduce first this mixture formation and quantification of mixing processes. And we'll give some examples. So to carry out evaporation, to describe the evaporation process, we have to consider two processes. We can let us suppose that this is our liquid phase, our droplets. Within we have only liquid, and outside here, in the surrounding, we have gas. And if we have a transfer within this surface, then the temperature will be high and some quantity of this liquid can go out. Then we speak about evaporation process. The amount of mass fraction will come out as we have introduced it before. Then we have two regions to be considered. The first region is the internal part of the droplets. This is we have to model the heat and mass transfer within the droplets. And we have also to account for the process here, because this amount should come out, and then we will have a gas model which account for the heat and mass transfer between the gas phase and the droplet phase. In all this, we don't have very high temperature, very high temperature like in combustion. Then the dominant transport mechanism will be the diffusion and convection. It can be laminar or turbulent. Because this quantity will come out, it will build here a kind of layer. Then we have thickness of the layer around the droplets interface. And within this thickness, we have diffusive transport. It is strong, stronger than the turbulence one. And this is the boundary layer around the surface as we have introduced them, for example, without also considering the turbulent flow or the interaction. We did it by introducing the virtual mass and the Bassett force. Depending on the transported material, we can have the molecular boundary layer, gas, thermal boundary layer for heat, and viscous boundary layer if we account for the moment. Because we have to deal with layers, that is why we call this model the film model. So now we have to start first with the droplets model. This means the heat and mass transfer within the droplets. We can do it in different ways by considering some assumption for the heat, some assumption for the mass, and also some assumption for both. First, we can assume that the droplet surface temperature is uniform. It does not change with time. It is only assumption. One can do this, and this is a very strong assumption because the surface, the droplet surface temperature should change, but it can change, but it should change, but in a uniform way. And they say not with time. That is very strong assumption. So the model is based on the assumption that we have also no temperature gradient inside our droplet. This means that we have infinity heat transfer within the droplets. This is the so-called infinite thermal conductivity. So there is no gradient, and the heat transfer is processing with infinite velocity, so it is very high. This is also not really, sometimes people use this, but it is very strong. So model which account for the finite thermal conductivity, not the recirculation inside droplets, because if the droplet is heated, so the effect of temperature can produce recirculation within the droplets. We have also another assumption which account here in this assumption, this is called the convection limit. If we have both, we have finite liquid thermal and we have the recirculation, then we speak about the effective conductivity models. We have also models, so-called vortex models, which account for the recirculation inside the droplets in terms of vortex dynamics, so within. And we have a very strong, very clear description of the droplets model. This is the model based on the full solution of the Navier-Stokes equation. So this means of the continuity equation, momentum equation, and also energy equation on species equation. So normally these assumptions here, these models are normally used in CFD, and because they are all easier to implement. I will show you only one. So the solution of the Navier-Stokes equation within the droplets. This is nice if we have to deal with a multi-component, because the solubility and the volatility of the different species are different, so that you can have different events at the interface. So we consider here spherical symmetry. We have no liquid phase reaction, and we consider one the thermal and mass transfer. It is for the mass transfer here. We have the momentum equation, the species transport, and the temperature equation. So we have naturally this equation we have introduced before. Okay, time derivative, we have the convective part, and here we have our flux term, diffusion term, and here we have also the diffusion term in these two directions. We have due to the scalar flux here, and this one is the drag for the convective force, and here it is exactly what we know. It is the diffusion term, the convective term, excuse me. It is the convective. So for AdBlue, it is a mixture of urea and water, binary mixing, and we follow the evolution along this radial position for the species diffusion, and here for the thermal diffusion. And we see that at the beginning, what we have is that at the beginning we have the temperature, with the temperature only one part of the urea which will start to evaporate, and then the other part will evaporate at the end. So, but if the urea evaporates slower, then we have first the water which will start to evaporate. And then the urea starts to evaporate at the end. It is the same here. So we have the evaporation first of water. This is also the thermal diffusion. So we have also the diffusion of the evaporation, the diffusion of the thermal diffusion of water, and then we have the diffusion of urea, which reach a maximum here. And this was done at this temperature. So we have the urea mass fraction, and here we have the droplets temperature evolution. So the temperature evolution start first, there is heating, and then the temperature go, and we have the constant, and by the heating, and at this point, water start to evaporate, and then you have the urea then at the end evaporate and goes to the maximum where it is only the part which remain to be evaporated because we don't have water. Okay, if we have this, we see the evolution of the droplet temperature, the heating, the starting of evaporation, and the starting of the growth of the temperature, and the temperature remain constant. And this goes together with the evolution of urea mass fraction. So first we have water which evaporate, and the urea is starting to evaporate first, and then we have a strong evaporation of urea. And this is the phenomena which occurs within the droplets for the spatial diffusion and here for the thermal diffusion. Now we go to the gas phase model, the film model. For this, we have also two kinds of film. We have so-called the constant film model, the constant thickness, excuse me, and we have also the variable thickness. We will account for the effect of turbulence through the Reynolds number, and this will be introduced through the correlations. We have introduced the Nusselt's number, the Short number, and we have said that it was for the case where we have laminar flows, and if we have turbulence, we have correlations, making a dependency between the Nusselt's number, Short number with the Reynolds number, and the Prandtl number for this, and the Reynolds number and the Schmidt number for that. We have also to know where, because we will have here, we have the layer, that is our film, the temperature on the surface, the mass fraction on the surface, and very far from the surface, we have the condition, thermodynamic condition, which correspond to the thermodynamic condition of the surrounding gas. Then we have the temperature of the gas, we call it T gas infinity, or the mass fraction of this gas. Here we have the different thickness, the thickness of the thermal boundary layer, the thickness of the species boundary layer, and we have also the thickness of the momentum. Okay, for the mass, as we have introduced here, we have whether molecular boundary layer or we have the viscose or the thermal. So that is what I call molecular. It is the M, and it is the thermal. So what within now this film, the question will be how we will determine the material properties of this mixture, air vapor within the film. And for that, we have to put some guidelines and to define this reference state. But I would like only to point out here that if we have different boundary layers, we have also different processes. So if, for example, the boundary layer, the flow boundary layer is larger than the thermal boundary layer, yeah, this is the situation where the Prandtl number is positive, is larger than 1. If the boundary layer is very small, then the thermal boundary layer will be larger than the flow boundary layer. If we have the Prandtl number equal to 1, then these two will be the same. It is only for your information. So the first part is to see how we can account for the effect of turbulence. For that, we need some correlations. And to do this, we use the procedure introduced by Sajid, a colleague, and his paper. I refer to this paper somewhere here. So we start with this equation. So we have introduced this equation yesterday, I think. Okay. We have the heat transfer coefficient. And it was defined as this here. And it was related to the Nusselt's number. Yeah, we did it yesterday in this form. And this say, if we have defined this heat transfer in this way, so we did it also yesterday, this means that we have, if we have no turbulence, that the Nusselt's number is equal to 2 if the Reynolds number is 0. Okay. This means that you should have in each correlation 2 plus something, in which if we don't have the Reynolds number, we don't have a motion, then the Nusselt's number will be equal to 2. And this is this expression is valid for this range of Prandtl number and this range of Reynolds. And this expression was obtained from experimental work. We can also have another expression which is more complicated. This account for, we have this expression first, 1/3 and 1/3 and 1/2 divided by this quantity, where BF is given by this expression. This part is referred to what we have almost here. And we have these expressions where we have this ratio. We can derive this expression, but it is made in the paper by Sajid. We have two contributions here. We have the first one is the heat rate spent on rising the temperature of the liquid. So that is what we have seen here. We have a quantity of temperature which needed to raise the temperature of the liquid. And this quantity and this one, so they are the heat rate supplied to droplets by convection. This is convection, and this is by radiation, if we have also radiation in this. And the Reynolds number is clear for us. We know this. We have introduced this. And these separates are also known. So we have now two kind of correlations, this one and this one, but we have a series. I will show you, I will give you a table in which we will see how we can do it. In a similar way, we can also have the correlation with respect to the Sherwood number. We base on this equation in which we have introduced the mass transfer coefficient. And in this area, we introduce also the Sherwood number. And we can write this in this way. I think you remember the expression we got yesterday. And here also, it is say that if we have in a quiescent gas, then the Sherwood number should be equal for stationary droplets. So the Sherwood number will be equal to 2. That is why we have 2 plus something. And we can also have this quantity here. That is what we call the Spalding mass number. Okay. If we have these definitions, we can write them as a in the dependency of the mass fraction or of the mass of the density of the mass fraction. And how to do it, we can obtain this from the clear derivation. So I can provide this, but I think it is not necessary here the best, the essential thing is to get the expression and to have them as we do here. This expression is not only valid for this range of Reynolds number. This is the first way to account for the to account not only for the turbulence but also to account for the transfer of mass or transfer of heat. Good. Now the second way to deal with is to use the so-called hydrodynamic models. For that, we will solve additional equations that give the rate of change of droplet diameter and temperature. So from this quantity of heat, we can deduce the variation of the temperature of our droplets, and we can also deduce the quantity of mass evaporated from our liquid. And this is exactly what I have written here. The variation of this is the mass, is the evaporation rate. And if we consider spherical surface as spherical droplets, then we have this mass. And what is this? It is the mass of the particle multiplied by capacity coefficient multiplied by temperature of the particle, and we have the time derivation for exactly what we do. It is an equivalent expression to this one. So if we have this, we know the liquid phase and we know the interface, and we can then try to put everything together in order we can produce the equation. We can directly obtain this equation. So, but let me extend a little bit the expression we got before. This was this expression here, okay? And this expression was obtained based on some limitation. We say that we know the effect of convective flow of the mixture of gas and fuel vapor. This means that we have neglected the so-called the Stefan flow. It is the induced flow due to the effect of the mixture of gas and the fuel vapor away from the surface of the droplet. Now we would like to introduce the Stefan flow. This means the effect of the convective flow of this mixture of gas and fuel away from the surface. But we say that there is equilibrium between the flux, between the mass, which is coming at the diffusion, and this is the diffusion coefficient of the gas. And this U is the value of the net velocity of the mixture of gas and fuel away from the droplets. So if now we account for this effect, okay, this is the effect we would like now to use. We have to add this effect to this expression here, where we add only the thick low, as we did it yesterday, and we add this where the gas is for our vapor, and this is for our vapor too. And we put them together, okay? And here we replace this quantity by this one. And by integrating it, we obtain exactly what we have here. That is our evaporation model, in which we account for the Stefan flow. This expression can also be obtained if we go from the transport equation of energy. And from the transport equation of energy, we have this part, which is now, this is latent heat, and this is the quantity we need as we introduce it before here. This is the quantity we need to raise the temperature of the liquid. And by using this expression, then we can go back, we can go through and to solve it. So the details of solving are not given here, but we can do it. I gave only them the main part. And after integration of this expression, so in which we have introduced this quantity, what we introduced before. So then we have introduced here. Then we have exactly the expression. Let me see exactly what I am saying here. Oh, I didn't see it. Okay. So we have this expression, and this expression is transformed. The second set part show the heat spent on the drop and raising the temperature. And if we express them in another way, in which we make a separation of variables, so this part here goes here and this part goes there, and we integrate. After integration, we obtain this expression here after separation of variables. And we obtain this now as a function of BT, and BT is the Spalding heat transfer number. This means that this expression is equivalent to this one. It is equivalent to this one in which we have the Spalding mass transfer number. We put them together. The BT is given by this expression we are obtained from here. We can then obtain a relationship between BT and BM, and it is obtained in this way where phi includes the ratio of this CP and CP for the vapor and CP for gas, and we have here this Lewis number. It is this relationship here, what we have there. And if the Lewis number is equal to 1, this means that we don't have a relative diffusion process. Then we have this quantity is equal to BT, BT is equal to BM. If not, we have these differences. And we have difference between these two, and we have a relative diffusion. We have diffusion process, which is different, not only for the thermal and the mass, but we have also for different species if we have multi-component species. So we can solve this. And if we solve this, we will obtain that the Q dot S is this quantity. So this means that we are here. And if we solve this, we obtain this expression where Z is exactly what we have here. And why I would like to show this? I would like to show this because if we go back, we will obtain this expression, and this expression can be written as a function of this, QS. And if we have this, then we will get the relationship between the mass fraction, the evaporation rate, and the Nusselt's number, and also the Spalding, the thermal Spalding, the thermal Spalding number. And if we have this, we can try to introduce the Sherwood number at stationary, or perhaps other to say in another way. If we compare this expression, the expression 989, this expression, okay, and the expression 94. and this expression, we see that we don't have the effect of the Reynolds number. This means that we consider that we are in a stationary case, and for which the Sherwood number is equal to 2. In the presence of this flow, if we have a flow, the Stefan flow, then we need to use this equation and to get a relationship not in this form, but now in this form. And we go from this equation, and we make some transformation, and we obtain this expression. And if we compare both, then we obtain a relationship between the Sherwood number, we can call it effective Sherwood number, and the Sherwood number in the case we have a stationary case, or where we don't have Stefan flow. So this effective Sherwood number is equal to this, multiplied by the Sherwood number when the Stefan flow is not existing. This allows us, for example, to get to introduce in our previous expression. So to introduce, for example, to replace this expression by this expression here. And for that, we will get another expression here for 97, in which we will have the Sherwood number here multiplied by this, and this will be the effective Sherwood number. We will come to this later. So let's now show the evolution of the droplets size. We have this m dot evaporation rate. We have to introduce this quantity here in this expression there. And we know that we can write this in this form if we don't consider the Stefan flow. By doing this, we get exactly the expression we have here. And this is exactly what we have. But if we want to do it also in a very, very consistent way, we can introduce this here, and we say that the diameter and the density is time, it depends on the temperature of the droplets, and we will get this expression. But we say this quantity is negligible. Then we have the dependency between the time variation of the density of the diameter and the evaporation rate. We can introduce this evaporation rate here, and we will get this expression again. And solving this, we obtain d square is equal to this expression if we assume that this quantity is a constant. If we say that the Sherwood number does not vary considerably, and we have this expression what we have. And for that, we can also define the so-called the lifetime or evaporation time of a droplets. We say it is the time we need to get the diameter of the droplets vanishing. This means that d is equal to 0 in this expression here. And if we get it, then we can derive the time for the life of our droplets. And this is exactly the d square law. This law after initial transient period associated with the heating of the droplets near boiling point. So this is the d square law. It is sometimes verified for some processes. And before I give some some example. Let's show how we will get also the equation for the temperature of the droplets. We have this expression here, and from this expression we need only to put to write the dp dTp, the variation of the temperature of the particle with the time, and we put this here, and we say that m is the mass of a spherical droplets, and we get this expression. And if we know this expression here as we did it, we have two terms. We have the first term and the latent heat. And if also we replace this m dot by the expression we got here, in the case we have no Stefan flow, then we have this term and this term. And here we have the coupling between the mass transfer and the heat transfer. But in general case, we have this term, which is given as the first part to hit there, the particle or the droplets. We have also radiation term. We have the latent heat part, and here if we have reaction, we can also have the reaction part in this equation. So with this, we have two additional transport equations. We have the transport equation, the variation of the size of the particle, and the variation of the temperature of the particle. And with this, I summarize everything here. We have these two transport equations, the two additional transport equations we have first. As I told you, we could get the Nusselt's number and the Sherwood number as function of Reynolds number and Schmidt number, or as for the Sherwood number as function of the Prandtl number for the Nusselt's number. And in this expression, also we need to put, as we did it before, we have deduced this term. And if we have this expression, then we can include this term here, and then we have the expression we had. And we can see the deviation to the d-square law, and this is what we give in a few minutes later. So if the Stefan effect is considered, we have Lewis number and convection for variable thickness. Then we have this expression I told you. We add the effective Sherwood number here as this expression we obtain we have obtained here. We have introduced as here. And we have now the relationship with allow us to get the evaporation rate in the relation with the Spalding mass transfer number, and also the same, we obtain the same relationship with the Nusselt's number. So there are also now way to calculate these quantities. Okay, this is the BT or what is function as enthalpy here, but it is the temperature also. So the way to calculate this quantity here are provided by different models. And here I introduce the equilibrium model by Abramson and Sirignano. We use the way to calculate it, which in which the mass fraction at the interface is given by the mole fraction in equilibrium state, which is calculated with the Clausius-Clapeyron equation. So we have this equation and we have this mole fraction. If we have this mole fraction, then we can put here and we have this value. This is derived by the gas flow calculation, the Carrier phase flow calculation. But this can also be calculated by this expression as we have introduced before. This is the ratio of different capacity terms. To sum up, we have the momentum equation. We have this factor describe the departure from Stokes law and Stefan flow, which is 1. If we have Stokes law, it is also 1. In the case we have not Stefan flow or the blowing effect. We have the energy equation, so F we provided here. And from them we can have the expression for the temperature of the flow of the particle. It is derived from what we had, and assuming this relationship here, we can go from here to this expression. Okay. And these introduce the relaxation, the dynamic relaxation time. Yeah, due to this one, it is this quantity what it is now. We did this. We introduced this notation before, and here we have the density of the Fourier phase, and here we have the latent and this is our quantity we have introduced for the evaporation rate what we have here. So F2 is a factor correcting for evaporation effect. It accounts for the Stefan flow in the case of the evaporation, for evaporation, the thermal case, and the Q then is obtained exactly as we have obtained a Q that is obtained here as we have obtained exactly the M dot for the mass, for the evaporation. With this, let's put everything here together. We have this equation we obtain here. We have this expression we have obtained now. And this is our equilibrium model by Sirignano. The F2 is provided by this expression, this F2. Okay. Here I give only the expression. So the details can be obtained in this paper. So we have F2, we have BT, we got this expression here, and phi is given by this expression where we have a dependency with the Lewis number, and we have also our Nusselt's number is equal to 2 plus this if we are in a stationary case, then it is equal to 2. So this is Sherwood number star is also the effective Sherwood number, and this Sherwood number, so we got these correlations, and this function is a function also for Reynolds number. This can be in this way, and the Lewis number in the tiles is provided by this. So we can also have the so-called non-equilibrium model. It is for very, very small particle in which the Lassus-Capron equation is no more valid. And here we introduce the so-called Langmuir-Nusselt consideration. We have F2 will now have this form in which BT is given by this expression, and FT is provided by this relationship here, so that we have a very complex formulation of the evaporation model. This is very widely used in the literature. Sometimes this, but we use this also for some combustion processes where the droplets are very fine and we have high temperatures so that non-equilibrium situation occurs. We have now the way to estimate. We say at the beginning that we have also to estimate the quantity of this thermophysical quantity within the layer, and this is what I've spoken about this here. So to define determine the material properties of the mixture within the film. For that, we use the so-called 1/2, 1/3 or 1/2 model. So this is what we have. We have our droplets. It evaporates. We have this layer, and this is the radius of the droplets. This the radius of the total radius, and here we have this different thickness. So within this region here, how we can determine the material properties. So the material properties we will obtain here, we will call them the reference values. And to get this reference value, we use this rule. We have the value in infinity plus 1 ratio multiplied by the value here on the interface minus what we have here. And this rule can be 1/2 or 1/3. Normally, this is commonly used, but it depends also on the situation. We use this one here, and for that, we obtain for the temperature, it's evolved, and we have this value of the temperature. This is the temperature in infinite, and this is the evolution of the temperature. Okay, and for the mass fraction, it is decreasing. So then we have this, and we consider that we have with ideal gas environment. All what I have said everything, and we assume that the interface, we have saturation values. And here we have the gas environment, the temperature here, infinity. So the value for the mass fraction is here, and for the temperature will be there, defined using these rules. And with this rule, we can now say that if we use these rules and we define their correlations in this way, experimentally, so there is some correlation for their case with constant thickness and with variable thickness. With constant thickness, we have this value. And for variable thickness, we have this effect of the variation of the thickness. And we have different correlations and using different reference expressions. And it is also valid in a different range of Reynolds number. And we have this expression here, for example, and also here we have this expression also for the correlation of the Shelf number under condition where we neglect the droplet vaporization. This means we neglect the Stefan flow. So we have a series of these. Yeah, normally this is sometimes used this year, sometimes also other use this, but it depends on the configuration we are investigating. The drag force change also because we the radius of our particle is changing, then the drag force will also change with this diminution. This means that we have the drag force here for non-evaporating and for evaporating. We have then the this value will depend on this one, for example, this case, in which we have this effect of evaporation here, the effect of the evaporation process. So this is the BT or BR, and the other correlation are here. And sometimes people use this, and the people also use this, but we can use what we use normally is the Marshall correlation. It is not here, but I will give you in one example I will show. So now with this, I think I will give some example here for evaporation process, and perhaps it is better to start this tomorrow because I see that the time is running, and we will start with this and then give some example and continue then with the modeling, the dispersion model, and also different other kind of models, and then to combustion. I thank you, and I think you have some time to put your questions.
Hello. Everyone, can you just post your questions so that Professor Sadiki can answer?
So you can write or say it directly. I think it is also okay.
Yeah, I mean, yeah, that would be fine actually. If anyone has any questions, they can raise their hand so that I'll just allow them for their talk. So yeah. I think I don't see anyone having any doubts.
So I sent the manuscript so they can see them. They can see it, and perhaps tomorrow they will have some.
Yeah, sure. So,
okay. Thank you, everybody. We will meet tomorrow.
yeah. So yeah, we will then meet tomorrow. Thank you, Professor Sadiki, for the talk. And
I'll see you tomorrow. Thank you.
yeah, we'll see you.